Okay, let's dive right into this. Welcome to The Explainer. Today we're exploring ARPANET and the literal birth of the Internet. We're going to uncover the hidden plumbing of the digital world.
You know, the very technology you're using right now to watch this, it didn't just magically appear out of thin air. It was actually born from a 1960s Cold War defense project. Back in 1958, the Advanced Research Project Agency, or ARPA, was formed as a direct response to rising global tensions. And looking back at the source documents from that era, the paranoia was incredibly real. The U.S. Department of Defense was staring down the looming threat of nuclear strikes, right? So they were urgently looking for a highly survivable command and control system. Basically, they needed a communications network that couldn't just be wiped out by a single, well-placed attack.
And this brilliantly illustrates the timeline of how they tackled that massive problem from the 1950s through the 1980s. You see this incredible convergence of ideas. We've got visionary minds like J.C.R. Licklider, who is already pitching this wild idea of a universal, galactic network. Then there's Paul Baran at the RAND Corporation and Lawrence Roberts, who managed the ARPANET program. What's truly amazing here is that they were all independently wrestling with the exact same massive puzzle. How in the world do we build a nationwide network that won't immediately fail if a single cable gets cut or a whole city goes dark?
Well, the answer they arrived at was this revolutionary concept called packet switching. Donald Davies over in the UK and Paul Baran in the US really pioneered this. And honestly, it must have felt so counterintuitive at the time to intentionally chop up important data. But think of it like taking a massive, heavy novel, tearing it up into hundreds of individual postcards, numbering them, and then mailing them all separately to the exact same destination through different post offices. Instead of taking one dedicated truck, they travel via completely independent routes. You know, some might fly, some take the train, but once they all finally arrive, the person on the other end reads the numbers and reassembles them back into the original book. That is packet switching in a nutshell.
To put that into perspective, just contrast the old centralized networks with the new decentralized ones. A centralized network relies on a single, vulnerable hub. It's a massive single point of failure. If that central hub goes down, the whole system goes completely dark. But a packet switch network is a decentralized web of nodes, and this was exactly what the Defense Department needed. It meant that national communication could actually survive. It could dynamically reroute all those digital postcards, even if major network nodes were literally destroyed in an attack. The network just kind of finds another path.
So, by 1969, ARPA hired a company called Bolt, Beranek, and Newman, or BBN, to actually build this thing. And here we can see a map of a typical early packet switching network. BBN built what they called interface message processors, or IMPs, which acted as the very first packet switches. Now, these weren't the sleek little Wi-Fi routers sitting in your living room today. No way. These were giant refrigerator-sized machines. They connected the host computers together and were the absolute crucial piece of hardware that proved packet switching could actually work out there in the real world.
But as ARPANET grew and other independent networks started popping up globally, a massive new hurdle emerged. How do you connect networks that speak entirely different languages? By the 1970s, this was literally known as the internetworking problem. We had built these brilliant networks, sure, but they were effectively isolated islands. A computer on a satellite network couldn't easily share resources with one on a ground-based radio network. It was like trying to get a group of people who all speak different languages to coordinate a highly complex project without a translator.
Enter two computer scientists, Vinton Cerf and Bob Kahn. Looking at their landmark 1974 paper, you realize they formulated a brilliant protocol to solve this exact communication barrier. They called it the Transmission Control Program, which eventually evolved into the TCP/IP protocol suite that we still use every single day. It's just amazing to read their original thoughts, because their goal was simple but incredibly ambitious: allow wildly different networks to intercommunicate effortlessly, totally regardless of what hardware they were running on. To pull this off, Cerf and Kahn introduced a genius concept: the gateway. Instead of just a single isolated subnetwork, imagine multiple networks interconnected by these gateways. Instead of forcing every single computer in the world to learn the specific, unique language of every other computer, the gateway acts as a universal translator right at the border. It handles these inter-network packets in a totally standard format, smoothly passing data between completely different networks without needing to translate every individual computer's protocol. It was a real game changer.
So the crucial point is how this actual transmission works step by step. First, the source computer slaps an internetwork header onto its data, basically sticking a universal mailing label on the package. Second, the packet travels through its own local network until it hits a gateway. Third, and this is the brilliant part, if the next network can only handle smaller data sizes, say it's moving from a huge optical line to a slow radio link, the gateway actually fragments the packet. It chops it up into smaller, manageable pieces for that specific leg of the journey. Finally, the destination computer receives all these fragments and puts the original data back together. These gateways just seamlessly route our digital postcards right across international and technological borders.
Now, what's really interesting about this slide is we're looking at the literal blueprints of an internet data packet, pulled right out of Cerf and Kahn's 1974 paper. This is that internetwork header. You can clearly see the fields mapped out: the source, the destination, a sequence number so the receiving end knows exactly what order to sort the arriving packets into, a byte count, and finally, the actual text payload. This standardized format was the magic key. It meant every network could finally talk to every other network because they all essentially agreed to wrap their data in this exact same universal envelope.
And zooming in just a bit further on the data structure, we see the TCP identifier. See, a single computer might be running multiple processes at once, like maybe a file transfer and a remote login happening at the exact same time. The network needs to know exactly which process gets which incoming data. This is a fundamental task called multiplexing. Think of it like a giant apartment building, right? The network address gets the data to the correct building, but this TCP identifier acts as the apartment number. It ensures that the arriving bytes are successfully sorted and delivered to the exact right process inside that receiving computer.
Now let's trace the explosive growth of this technology. The TCP protocol was formulated in 1974. Fast forward to 1977, and researchers pull off an absolutely incredible internet working demonstration. It was this massive technological triumph where they successfully linked the ARPANET, a packet radio network, and a satellite network together across vast distances. And then came January 1st, 1983, known in the networking world as Flag Day. On this exact day, TCP/IP officially became the standard protocol for the ARPANET, fully replacing all the older software. That moment was effectively the birth of the modern internet as we know it.
As this infrastructure spread, the cultural impacts were absolutely massive, and honestly, wonderfully unanticipated. For instance, the network was built primarily for serious, high-level resource sharing. But a little unplanned, casual feature called electronic mail completely took over. It surprisingly hijacked the network, growing to account for a whopping 75% of all traffic. The system became truly global, with satellite links connecting nodes like Norsar all the way in Norway. And, in an amazing milestone, Queen Elizabeth herself even sent an email in 1976. By 1983, the network was so incredibly vital that it officially split into a civilian research arm and a separate military arm.
By 1990, the original ARPANET had successfully proved its brilliant vision and fully transitioned its users onto the modern commercial internet. Its job was done, and the whole shebang was formally decommissioned. Vinton Cerf actually wrote a poetic lamentation for the occasion titled Requiem of the ARPANET, where he beautifully wrote, "Lay down thy packet now, O friend, and sleep." It was a fitting, almost emotional end to a bold research project that literally changed the trajectory of humanity.
From a paranoid Cold War defense project designed to survive a nuclear disaster, we somehow gained the ultimate tool for global human connection. Which leaves us with a fascinating question to ponder as we wrap up. What will the next 50 years of networking look like now that we've laid this incredible foundation? Thank you for exploring this remarkable history with me. I hope this explainer helped you see the digital world around you just a bit more clearly and gives you a deep appreciation for the hidden plumbing of our lives. Keep learning, and I'll catch you next time.